There are two walls in the universe that no one can ever cross. One is the speed of light. The more you chase it, the further it leaves you behind. The other is absolute zero, minus 273.15 degrees Celsius. At this temperature, atoms barely move. Time feels like it's been put on pause. But the strangest part is this: even if you cool something down to the very end of the cosmos, true stillness is impossible, because behind absolute zero hides the most terrifying rule of the quantum world. Have you ever thought that temperature isn't really what you think it is? We grow up learning that temperature is just hot and cold. Hot means high, cold means low. But in real physics, temperature isn't a feeling, it's the speed of atoms. Every single atom is constantly vibrating, colliding, racing around. The heat you feel is just the kinetic energy of billions of atoms bumping against your skin. The higher the temperature, the faster the atoms move. The lower the temperature, the slower they move. So logically, there must be a limit, a point where atoms come to a complete stop. That point is absolute zero. But here's the problem. It took humanity hundreds of years to truly understand what cold even is. In 1714, a German man changed history. His name was Gabriel Fahrenheit, a self-taught physicist. He used a mixture of ice and water and human body temperature as two reference points, divided the space between them into 100 equal parts, and created the first usable thermometer scale. Back then, people thought that was good enough. No one wondered about the ultimate limit of cold. In 1742, a Swedish astronomer named Anders Celsius went further. He set the freezing point of water at 0 degrees and the boiling point at 100 degrees. Simple, elegant. That's the Celsius scale we use worldwide today. But these scales were just lines drawn for human convenience. 0 degrees Celsius doesn't mean anything special in reality. The real answer only began to surface 100 years later. In 1802, a French chemist named Joseph-Louis Gay-Lussac discovered something bizarre. While experimenting with gases, he noticed that the volume of a gas changes with temperature, and it follows a strict linear relationship. For every 1 degree Celsius drop, the volume shrinks by about 1/270th of its original size. What did that mean? It meant that if you follow that line all the way down to lower and lower temperatures at roughly minus 273 degrees Celsius, the volume of the gas would shrink to zero. Volume zero means no atomic motion, means everything stops. Gay-Lussac was shocked. The end of this line pointed directly to a physical limit built into the universe itself. That temperature is absolute zero, minus 273.5 degrees Celsius. It's also the 0 point of the Kelvin scale, called 0K. The Kelvin scale was designed specifically for this purpose. It has no negative numbers. 0K is the true zero, the coldest possible place in the cosmos. And from knowing it existed to actually getting close to it, that took another 200 years. So why is it so hard to approach absolute zero? Because cooling is far more counterintuitive than you think. Heating up a glass of water is easy. Just light a fire and pump energy into it. But to cool that same water down, you have to pull heat out of it and dump it somewhere else. And the closer you get to absolute zero, the more stubborn heat becomes. It resists being removed. The energy you need to keep cooling actually increases. This isn't a technical problem, it's the third law of thermodynamics, an iron rule written into the fabric of the universe. You can never truly reach absolute zero, only get infinitely close. But what happens when you get close? That's where the story gets truly mind-bending. Scientists discovered that when certain metals are cooled to near absolute zero, their electrical resistance suddenly disappears. Not just becomes very small drops to exactly zero. Electric current can flow in a closed loop forever. No power source needed, no energy lost. This phenomenon is called superconductivity. Today's Maglev trains float above their tracks using superconductors, no friction, no loss, silent gliding. Superconducting power lines could, in theory, eliminate all transmission loss, saving humanity trillions of kilowatt hours every year. And then there's something even stranger. Helium gas, when cooled to minus 269 degrees Celsius, becomes a liquid. Cool it further, and that liquid turns into what's called a superfluid. A superfluid has no viscosity. It can climb up and out of its own container. It can seep through microscopic cracks that should be impossible to pass. This isn't magic, it's quantum mechanics showing up in the macro world. But the thing that drives scientists absolutely insane is the existence of a fifth state of matter. We all know solids, liquids, gases, and plasma, but in 1925, Albert Einstein and an Indian physicist named Satyendra Nath Bose theoretically predicted a fifth state, the Bose-Einstein Condensate. They said that if you cool certain atoms to within a hair of absolute zero, those atoms would lose their individual identities. They would merge into one giant superatom, all behaving as a single quantum object. At the time, no one believed it was real. Then, in 1995, American scientists Eric Cornell and Carl Wieman used laser cooling techniques to cool rubidium atoms to just 170 nanokelvin above absolute zero, and they created the first Bose-Einstein condensate. These atoms existed in multiple places at once: quantum superposition, quantum entanglement, all the bizarre phenomena you thought only happened in the microscopic world now visible with the naked eye. A 70-year-old prophecy became reality in that moment. You might ask, what does any of this have to do with me? The answer is, a lot. The heart of a quantum computer is built on quantum effects that only exist at extreme cryogenic temperatures. Today's most advanced quantum computers operate at temperatures colder than deep space, just 0.015 degrees Celsius above absolute zero. They can solve problems that would take classical computers millions of years. The atomic clocks inside GPS satellites rely on ultra-low temperatures to maintain precision off by only 1 second every 300 million years. The superconducting magnets in the Large Hadron Collider accelerate particles to nearly the speed of light, recreating conditions just after the Big Bang and probing the deepest secrets of matter. Humanity approaches this wall, the wall called absolute zero, not to conquer it, but because the closer we get, the more we can see the deepest rules of the universe. Absolute zero is a finish line we can never cross. And yet, it is that very impossibility that pushes us, step by step, toward the infinite.